phrase to end right here, but not here. In other words, why is this chord more comfortable to end on?
Let's start with the physics of sound. Sound is a wave, which means that it transfers energy through the vibration of particles. This is what we get when we plot the position of any one vibrating particle over time. And we can describe this wave using its frequency, which is the number of cycles it can go through in a second. This example wave has a frequency of 2 Hz. Our ears recognize frequencies as pitches. A high pitch has a high frequency, and a low pitch, low frequency.
Going back to music, a chord is simply a collection of pitches. And when we examine the differences in frequency between these pitches, we find whole number ratios. So in this nice sounding D major at the beginning of the video, D has a frequency of 147 Hz. And a major third up, we have F sharp with a frequency of 185 Hz. This is a ratio of 4 to 5. A fifth up from D, we have A with a frequency of 220 Hz. And this creates a frequency ratio of 2 to 3 with D. And lastly, octaves have a 1 to 2 ratio, which means that this higher D has a frequency of 294 Hz, exactly double that of the lower D. Notice that all of those ratios were small whole number ratios, and that these pitches together created beautiful harmony. If we dissect the other chord from the beginning of the video, we notice a tritone from G to C sharp, which has a frequency ratio of 32 to 45. We also have a minor second from C sharp to D, and this has a frequency ratio of 15 to 16. Although these are still whole number ratios, they are more complex, so our ears recognize that the frequencies don't go as nicely together. So the next time you're listening to the end of a phrase or the end of a piece, you can think of the progression of chords as a progression from complex frequency ratios to simpler frequency ratios. Alright, there you have it. That's physics of beautiful harmonies.